Hello, physics students. This is Dr. Brinzy. We are on lesson 2.2.4, and our topic for today is drag force. So when I described what drag force is, we learned that drag force occurs when an object moves through a fluid. And in physics, a fluid can be a liquid or a gas, so air would count as a fluid in physics. So collisions between molecules in the fluid and the object create a force that acts against the direction of motion. And you've all experienced this when you stick your hand out a car window, and since you're traveling through the air at a pretty high speed, you experience lots of collisions of air molecules with your hand. And all those little air molecules, when they collide with your hand, will exert a force that pushes your hand backward. Now, unlike any other force that we've dealt with so far, drag force can be a little bit of a tricky force to deal with because it depends on the velocity that you're traveling. So when your velocity is low, the drag force is equal to some constant times the velocity that you are traveling at. Now, you might be asking, well, what is this constant? Well, this constant depends on a lot of factors. It depends on the shape of the object. It depends on how much surface area, what we call surface area in physics, is presented to the wind. So, like, think about it this way: if you put your hand vertical as you're traveling through that car, you are going to experience a lot more drag force than you would if you put your hand horizontal, so that the hand, in a sense, cuts through the air. So that basically what it comes down to is that engineers and physicists have to do a lot of experimental measurements to figure out what this coefficient K is, and it changes from one object to the next. So there really is no uniform set value for this K. So examples of when we could apply this formula for the drag force is when there's, like, say, a pebble sinking in a pond. So if you throw a pebble in the pond and then you notice that as soon as it hits the water, it immediately decelerates, and it's decelerating because it is going through water and it's experiencing drag force with the water. Or if you walk in a swimming pool, you know that there is a huge drag force when you played Marco Polo with your friends in the swimming pool, because it was really tough for you to walk through that swimming pool, and that's because there was a drag force that was exerted on you by the water molecules in the pool. When the velocity is high, however, drag force no longer depends on velocity, it depends on velocity squared. So not only does drag force depend on velocity, but the formula changes when you get to higher velocities. So examples of when the velocity is high might be when you're traveling down a highway in a car, or when you're on an airplane or in an airplane. Actually, it's the airplane traveling through the air that experiences drag force. When you throw a fastball, or when you're a skydiver. So those are all examples of when this formula would be more appropriate to use for the drag force than the one that you just learned in the previous slide. Okay, so there are situations where you have to apply this formula for drag force, and there are other situations where you have to apply the other formula for drag force. And it depends on whether the velocity is low or the velocity is high. So let's think of an example here. A swimmer experiences a drag force of 50 newtons while she is swimming at a speed of 2.5 meters per second. What drag force will she experience if she doubles her speed? Okay, now in this particular case, since our speed is low, we are going to use the F drag equals KV equation. And let's go ahead and enter the force. The drag force she experiences is 50 newtons. That equals this constant K, we don't know what that is, times her velocity or her speed, which is 2.5 meters per second. And when we solve this for K, we get 50 divided by 2.5, or we get 20. So, if I want to double, or if she wants to double her speed, that means she's going to double this number. So 2.5 times 2 will give me 5. So that's the new velocity that I plug in to my drag force formula. I know the value K now because I calculated it using the information that was given to me. And now we can calculate drag force. So that's equal to 20 times 5, which is 100 newtons. Okay, so that's one way that you could have figured out the drag force when she doubled her speed. But there's also another way, through a little what we call dimensional analysis. We know that I can manipulate this equation right here, divide both sides by V, so I get K by itself equals the drag force divided by velocity. And this constant K doesn't change with velocity, doesn't change with drag force. So it should be independent of what my velocity is and what my drag force is. So if I choose to double my velocity down here in the denominator to change V to 2V, what do I have to do to the drag force so that this constant K remains constant, doesn't change? Well, hopefully you figured out that I would also have to double the drag force. Okay, so if I double the velocity, I double the drag force. That will allow the constant K to remain constant. And let's see, 2 times our original force, our original drag force of 50 newtons gives us a drag force of 100 newtons. So that would be an independent way that you could figure out what the drag force is. All right, one more example here. So we have an airplane that experiences a drag force of 12 kilonewtons as it travels through the air at 150 meters per second. What speed must the airplane go if it wants to cut this drag force in half? All right, well, let's write down our drag force at high speed this time because we're going 150 meters per second. And you might be wondering, well, Dr. Brinzy, what's the cutoff? I would probably say, I'd probably use this formula, the high speed formula, when your velocity or speed gets above, I would say 30 meters a second. That would be a pretty decent cutoff. Okay, so we're going to use the high velocity formula for drag force, and let's go ahead and plug in what we know. We know 12 kilonewtons, so that's 1.2 times 10 to the 4th newtons equals our constant d times 150 meters per second squared. Okay, well, that's equal to d times 2.25 times 10 to the 4th. All right. So let's go ahead and find d by dividing both sides by 2.25 times 10 to the 4th. And when I do that and simplify, I get a value d equals 0.53. Okay. Now that I found d, I can go ahead and cut this drag force in half. So instead of 1.2 times 10 to the 4th, I have 0.6 times 10 to the 4th. I could have written that as 6 times 10 to 3, but it would have been easier this way to show you that I actually did cut the drag force in half. Well, that equals 0.53, which is my drag constant, times v squared. All right, so v squared there, divide both sides by 0.53, and I get 1.125. Let's see. 1.125. Let's see here. Oh, yeah, okay. I wrote this out a funny way. Let me back all this up. Because, all right. It's not 1.125, it's 1.125 times 10 to the second. I don't know why I wrote things in that order. Okay, and then when I take the square root of that, I end up with, I believe, 106. Okay, so 106 meters per second is my velocity. Let me put some units on that thing. Alright, so that is, let's see here, hold on here. Not sure what it's rating there. Okay, so V equals 106 meters per second. Alright, and that's the velocity that I came up with. So in order to cut this drag force in half, this person has to travel at a speed of 106 meters per second in their airplane. You know, we can use a little bit of dimensional analysis the same way that we used dimensional analysis in the last example. So if we want our D, drag coefficient, to remain constant, then we know that that drag coefficient equals D equals the force divided by V squared. And if I want to cut the force or multiply the force times 0.5, then I also have to multiply V squared times 0.5. Oops, forgot my force here. Okay. And when I do that, I get 0.5 F sub D divided by, now this might be a little bit tricky here, but what I'm going to do is say the square root of 0.5 times V, and then I'm going to square that whole thing. Now, in order to convince you that I have the right answer, imagine taking this and taking the square of it. So whenever you take the square of a radical, it just gives the radicand, the number inside the radical, which is 0.5. Okay, and then when I take V and I square it, I get V squared. Okay, so what this means is that if I want to multiply the force by a factor of 0.5, so if I want to cut the drag force in half, I have to multiply my velocity times the square root of 0.5, and the square root of 0.5 happens to be about 0.7. So if I take 150 times 0.7, I get 106, which is the same velocity that we got by figuring out what the actual drag constant is. Okay, that's it for this video, and look forward to seeing you soon where we can practice working with drag force. All right, talk to you then. Bye.